When people first hear the word empty, they imagine nothing at all. No objects, no motion, no events, just silence. That idea feels natural, because in daily life, emptiness usually means absence. An empty room has no furniture. An empty glass has no water. An empty street has no cars. So it seems reasonable to extend that idea to the universe and say that empty space is simply where nothing happens. That idea is wrong. It is deeply wrong. And what makes it interesting is not that it is wrong in a subtle way, but that it is wrong in the most dramatic way possible. Empty space is not quiet. It is not calm. It is not passive. It is one of the most active, restless, and energetic things we know. To understand why, we must first slow down and agree on something important. Physics is not about fancy symbols written on blackboards. Those symbols are only a language. Physics is about how nature behaves. The job of physics is to describe patterns in the world in the simplest and most honest way we can manage. When the description feels strange, it is not because nature is trying to be mysterious. It is because our everyday experience is limited, and nature is under no obligation to fit inside it. For a long time, people believed space was just a stage. Objects moved around on it, but space itself did nothing. This view worked beautifully for ordinary things. A thrown ball follows a path. The planets follow paths. If nothing pushes them, they keep moving. Space in this picture is just where all of this happens. It has no character of its own. That picture comes from classical physics, and it is still very useful. But usefulness is not the same as truth. When we began to study nature more carefully, especially at very small scales, we found that this idea of space as a passive background simply does not survive. The first crack in the old picture came when we learned that forces do not act magically at a distance. Instead, they are carried by fields. A field is not an object you can grab, but it is something real. If you place an electric charge somewhere, the space around it changes. That change is not imaginary. It can push on other charges. It can store energy. It can move. Once you accept fields as real, space stops being empty in the old sense. Even if there are no particles around, the fields are still there, and fields can vibrate. Light itself is nothing more than a vibration of an electromagnetic field. When a light wave passes through what we call empty space, something is oscillating. Energy is moving from place to place. That alone should make us suspicious of the word empty. But the real surprise came later, when we discovered that even fields cannot sit perfectly still. In classical physics, you can imagine a system at rest with exactly zero energy. A pendulum can hang motionless. A wave can be perfectly flat. A system can be quiet forever. This idea feels reasonable. If nothing disturbs the system, why should it move? Quantum physics tells us that nature does not allow this. The reason is not philosophical, it is mathematical, and the mathematics reflects experiments with extraordinary accuracy. At the heart of this lies a simple idea. To describe motion, you must describe change. To describe change, you need calculus. Calculus is not a monster. It is simply a way of keeping track of how things vary. How fast does something change? How smoothly? How much does it change over time? When you describe a wave, for example, you are describing something that goes up and down smoothly. Calculus is the natural language for that. Now here is the key point. In quantum physics, certain quantities are linked in such a way that if one is perfectly fixed, the other becomes wildly uncertain. One famous pair is position and momentum. If you know exactly where something is, you cannot know exactly how fast it is moving. This is not because your instruments are bad. It is because nature itself does not assign both values at once. There is a similar relationship between energy and time. If you insist that a system has exactly zero energy forever, then you are asking for something that quantum mechanics does not permit. The system must fluctuate. This leads to a remarkable result. Even the lowest possible energy state of a system is not zero. It has some unavoidable energy left over. This is called zero-point energy, but the name is less important than the idea. The idea is that nature never fully stops moving. Now apply this idea to fields. A field fills all of space. If it were completely empty and quiet, it would have exactly zero energy everywhere. Quantum mechanics forbids that. So the field must fluctuate. It must jitter. It must vibrate, even when no particles are present. This means that empty space is not empty at all. It is filled with fluctuating fields, constantly changing, borrowing energy and returning it, never settling down. These fluctuations are not large. Most of the time they average out. On average, space looks calm, but calm does not mean inactive. The surface of a lake can look smooth from far away, even while countless molecules are moving beneath it. Here it is important to understand what we mean by average. In advanced calculus, averaging is not a vague idea, it is precise. You add up all the possible values of a quantity, weighted by how likely they are, and divide by the total. This process hides a lot of motion. When you say the average height of the ocean is constant, you are not saying the waves stop. Quantum physics works the same way. Many quantities fluctuate rapidly, but when you look at them over time or over space, they settle into stable patterns. Stability does not come from stillness, it comes from balance. At this point, someone might ask whether these fluctuations are real, or just a mathematical trick. The answer is that they are as real as anything else in physics. We know this because they produce measurable effects. Even before discussing those effects, it is worth pausing to appreciate how strange this already is. We began with the idea that empty space is nothing. We replaced that with fields. Then we discovered that fields cannot be quiet. The result is that what we call empty space is a seething background of activity. And this is not speculation. It comes straight from the same framework that explains atoms, chemistry, and electronics. You do not get to keep the successful parts and throw away the inconvenient ones. Nature is consistent. Now let us return briefly to calculus, because it plays a silent but essential role here. When physicists describe fields, they describe how the field changes from point to point and from moment to moment. That description involves derivatives, which tell us how fast something changes, and integrals, which tell us what happens when you add up many small contributions. You do not need to perform these calculations to understand the idea. You only need to accept that nature cares about smoothness and continuity. Fields do not jump randomly from one value to another. They vary smoothly, like waves on water. Quantum mechanics does not remove this smoothness. It constrains it. Because of these constraints, the fluctuations of empty space have a characteristic structure. They are not chaos in the everyday sense. They are tightly regulated by mathematical rules. This brings us to an important lesson. When physicists talk about randomness, they do not mean disorder. They mean unpredictability within strict limits. A dice roll is random, but the dice does not suddenly turn into a bird. Quantum fluctuations are random, but only in ways that preserve the underlying structure of the theory. Empty space, then, is not a place where anything can happen. It is a place where very specific things happen all the time. Why should anyone care about this? Because these fluctuations are not just philosophical curiosities. They influence the behavior of real objects. They affect how atoms behave. They contribute to forces we can measure. They play a role in the stability of matter itself. In fact, if empty space were truly empty, atoms would not behave the way they do. The energy levels of electrons would be different. Chemistry would change. Life, as we know it, would not exist. This may sound dramatic, but it is simply a reminder of something physics teaches again and again. The familiar world depends on deep and unfamiliar rules. One might still feel uneasy. After all, if empty space is full of energy, why does it not overwhelm everything? Why does the universe not explode? The answer lies in symmetry and balance. For every fluctuation in one direction, there is typically another in the opposite direction. Over large scales, these effects cancel out. What remains is a subtle background influence, not a runaway catastrophe. Think of it like the pressure of air. Individual molecules are constantly colliding with your body at enormous speeds, yet you do not feel battered. The forces balance. Only when there is an imbalance, like a pressure difference, do you feel a wind. Empty space behaves in a similar way. Its activity is mostly hidden, because it is uniform. But uniform does not mean trivial. As we continue, we will see that under the right conditions, this hidden activity reveals itself in surprising ways. But even before reaching that point, we have already learned something profound. Nothingness, as a concept, does not survive contact with reality. The universe does not tolerate absolute emptiness. Wherever there is space, there is structure. Wherever there is structure, there is motion. And wherever there is motion, there is energy. This is not poetry. It is a summary of what experiments tell us. When we listen carefully and follow the mathematics,
where it leads. In the next stage of this discussion, we will look more closely at the entities that inhabit this restless background, and at the strange bookkeeping rules that allow them to appear and disappear without violating the fundamental laws. For now, it is enough to let go of the old idea that nothing means nothing. In physics, nothing is often the most interesting thing of all. If we accept that space is full of restless activity, the next natural question is simple. What exactly is doing all this moving? We have said that fields fluctuate, but that word can feel vague. So let us be more precise, while keeping our feet on the ground. In modern physics, the most basic ingredients of nature are not particles, they are fields. A particle is best thought of as a small localized vibration of a field, much like a wave on the surface of the ocean. The ocean exists everywhere. The wave is something special happening in one place, for a short time. This idea takes some getting used to, because we are trained to think of particles as tiny solid objects. But experiments force us to abandon that picture. When we try to pin a particle down too precisely, it spreads out. When we let it move freely, it behaves like a wave. The most honest description is that a particle is an event, not a thing. Fields, on the other hand, are always there. Even in regions where no particles appear, the fields remain. They fill space completely. Each type of particle corresponds to its own field. There is an electron field, a photon field, and so on. Empty space means that none of these fields are excited enough for us to see a particle, but the fields themselves never disappear. Because of quantum rules, these fields cannot remain perfectly quiet. They are always trembling slightly around their lowest possible energy state. This trembling is not optional, it is built into the structure of the theory. Now here is where the story becomes truly strange, but also very precise. When these fields fluctuate, they sometimes behave as if particles briefly exist, and then vanish. These are often called virtual particles. The name is unfortunate, because it makes them sound imaginary. They are not imaginary, they are internal events allowed by the mathematics, and their effects are real and measurable. The key idea behind this is again linked to the relationship between energy and time. If you borrow a small amount of energy for a very short time, nature allows it, as long as you give it back quickly enough. This is not a loophole in the law of conservation of energy. It is how the law works at small scale. Think of it like balancing your checkbook over a month instead of a second. If you briefly dip into negative balance but fix it quickly, the overall accounting remains correct. Nature keeps perfect books, but it allows temporary fluctuation. As a result, the vacuum is full of brief events, where fields act as if particles pop into existence and then disappear. These events cannot be observed directly as particles flying around, but they influence how real particles move and interact. One of the clearest demonstrations of this comes from a very subtle force that appears between two metal plates, placed extremely close together in a vacuum. When the plates are far apart, the fluctuations of the fields push on them equally from all sides. But when the plates are close, some fluctuations are excluded from the space between them. The result is an imbalance, and the plates are gently pushed together. This effect is tiny, but it has been measured with great precision. Nothing mysterious is being invoked. It is simply the pressure of fluctuating fields in what we used to call empty space. This should convince us that these fluctuations are not just mathematical decorations. They have consequences. They push, they pull, they change energies, they alter forces. At this point, it is useful to revisit the idea of chaos. In everyday language, chaos means disorder, but in physics, chaos often means sensitivity. Small changes can have large effects, but the underlying rules remain strict. The fluctuations of the vacuum are chaotic in this technical sense. They are unpredictable in detail, but predictable in their statistics. We cannot say exactly what the field will do at a given instant, but we can say what it will do on average. Advanced calculus is the tool that allows us to make sense of this. When we cannot track every tiny fluctuation, we do not give up. We sum over all possibilities. We calculate averages. We compute probabilities. An integral in this context is simply a way of adding up contributions from all possible configurations of a field. Each configuration has a weight, which tells us how likely it is. The final result is not one outcome, but a pattern. This way of thinking is deeply counterintuitive, but it works. It predicts experimental results, to astonishing accuracy. There are calculations involving these vacuum fluctuations that agree with measurements to more than 10 decimal places. That is not luck. That is evidence. Now one might reasonably worry that if empty space is full of energy, then this energy should gravitate, it should curve space and time. Why does it not dominate the universe? This question leads us into deep territory, and we must tread carefully. The honest answer is that we do not yet fully understand how vacuum energy interacts with gravity at the largest scales. This is an active area of research. What we do know is that only differences in energy usually matter. A uniform background often has no observable effect locally, just as a constant atmospheric pressure does not crush us. A constant vacuum energy does not necessarily distort local physics in obvious ways. However, on cosmic scales, something remarkable happens. Space itself is expanding. Galaxies are moving away from one another, not because they are flying through space, but because space between them is growing. This expansion appears to be accelerating. One possible explanation involves the energy of empty space itself. Again, we must be cautious. The details are subtle, but the idea that the vacuum plays a role in the large-scale behavior of the universe is taken very seriously. What matters for our discussion is not the final answer, but the lesson. Empty space is not a passive backdrop. It participates in the dynamics of the universe. Let us now bring this back down to a more familiar scale. Why does matter feel solid? Why do atoms not collapse? The answer involves a balance between forces and fluctuations. Electrons do not fall into atomic nuclei, because doing so would require confining them too tightly, which would increase their energy. This energy comes partly from the same quantum rules that make empty space restless. In this sense, the stability of matter depends on the same principles that make the vacuum active. The world we experience is not built on stillness. It is built on motion held in balance. This is one of the most important lessons physics has to offer. Stability does not come from freezing everything in place. It comes from dynamic equilibrium. Things move, fluctuate, and change, but in such a way that large-scale patterns remain stable. Once you see the universe this way, many puzzles dissolve. Instead of asking why there is something rather than nothing, you begin to see that nothing is an unstable idea. Given the rules of quantum physics, complete emptiness is not allowed. Structure is the default. This does not mean the universe had to exist exactly as it does, but it does suggest that existence is not as fragile as we once thought. The laws themselves favor activity. At this stage, it is tempting to reach for dramatic language, but it is better to stay honest. Physics does not tell us why the laws are what they are. It tells us what follows if they are, and what follows is a universe in which even the quietest places are alive with subtle motion, a universe in which calm is an illusion created by averaging over chaos, a universe in which the most basic level of reality is not made of things, but of relationships and changes. This way of thinking can feel unsettling, because it removes the solid ground we are used to, but it also opens up a new kind of clarity. Instead of clinging to simple pictures that break under pressure, we accept more flexible ones that survive. Science progresses not by making things more comfortable, but by making them more accurate. Comfort comes later, when we learn how to live with the truth. The picture we now have is not complete. No physicist believes that our current theories are the final word, but they are good enough to teach us humility. The universe is not obligated to match our intuition. Our intuition must be trained to match the universe. If there is one habit worth cultivating, it is curiosity, without fear. When an idea sounds strange, that is not a reason to reject it. It is a reason to examine it carefully. We began with the idea that empty space is nothing. We end with a picture in which space is a restless participant in everything that happens. Between these two views lies a great deal of mathematics, experimentation, and careful thought. But the heart of it is simple. Nature is subtle, but not malicious. If we ask clear questions and follow the evidence, we are rewarded with deeper understanding, and perhaps the most valuable reward is this: the universe is far more interesting than we ever imagined. Even in places where we thought there was nothing to see, there is an endless dance of possibility, quietly shaping everything we know.